A log, 60 feet long, 6 feet in diameter, weighing 100 tons, 200,000 pounds. It's lying on the forest floor where it was felled. It needs to be moved 2 miles to a landing where it can be loaded onto a railroad car. You have 10 horses, 50 men, some chains and cables, and a pair of wheels so large that a man standing next to them barely reaches the axle. The wheels are 12 feet in diameter, taller than a house, made of iron rims and wooden spokes thick as telephone poles. The axle between them is a solid iron shaft 18 inches in diameter. This contraption is called a logging arch or big wheels, and it's about to do something that seems physically impossible. Those 2 massive wheels are going to lift one end of that 100-ton log off the ground. The horses are going to pull it. And that log is going to travel 2 miles through the forest, rolling on those wheels, leaving a furrow in the earth where it passes. This was log transportation in the era of giant timber, from the 1880s through the 1920s, when the trees being cut were so large that moving them required engineering solutions that seem absurd until you see them working. Big wheels that lifted loads weighing more than locomotives, steam-powered winches that could drag logs a mile through the forest, horse teams of 20 or 30 animals hitched together, pulling weights that would break modern truck frames. The ingenuity wasn't in the trees themselves. The ingenuity was in figuring out how to move trees that God never intended to be moved. This was industrial logging in the Pacific Northwest California, and parts of the Great Lakes region, anywhere old-growth forest produced trees too large to be handled by conventional methods. A typical commercial log in eastern forests might be 18 to 24 inches in diameter and 20 feet long, weighing perhaps a ton. That could be handled by a team of horses or oxen using traditional methods. But the Douglas firs, redwoods, and white pines of the West Coast and Lake States were different. These trees might be 5 to 8 feet in diameter and produce logs 40 to 80 feet long. A single log from these trees could weigh 50 to 100 tons. Traditional methods couldn't move such weights. New technologies had to be invented. Could you really lift one end of a 100-ton log using just wheels and leverage? Could horses pull such a load? And could you do this economically, making it cost-effective compared to leaving the giant logs in the forest? The answer is yes. The evidence exists in photographs showing these massive wheels and the enormous logs they moved, in engineering records documenting the equipment specifications, and in the economic records showing that big wheels and steam donkeys made large log logging profitable. Before we get to the specific equipment, you need to understand the problem these technologies solved. Because moving giant logs wasn't just difficult, it was the primary limitation on harvesting old-growth forests. A log lying on the ground has tremendous friction with the earth. The contact area between a log and the ground might be 20 to 30% of the log's surface area. That creates friction proportional to the weight. A 100-ton log lying on soil might require 20 to 30 tons of force to start moving, to overcome static friction. Once moving, the force required drops to perhaps 10 to 15 tons for rolling friction. But that's still an enormous force, equivalent to pulling 10 fully loaded wagons. The traditional method for moving logs was ground skidding, hitching horses or oxen to the log with chains and dragging it along the ground. For small logs, this worked. For large logs, it was impractical. The friction was too great. The log would dig into the ground rather than sliding. Obstacles like rocks or stumps would stop the movement. The distance you could move large logs by ground skidding was limited to perhaps a few hundred feet at most. The solution in principle was simple: reduce friction by getting the log off the ground. If you could lift one end of the log, only the other end would drag. If you could lift both ends, the log could roll on wheels. The challenge was engineering equipment strong enough to do this lifting, while remaining portable enough to work in the forest. The big wheels, also called logging arches or log wheels, were the first successful solution. The concept was to create wheels large enough and strong enough that they could be positioned over a log. The log could be chained to the axle, and the whole assembly could be pulled forward with the log suspended between the wheels. This reduced friction dramatically because the log rolled on wheels rather than dragging on the ground. The construction of big wheels required both massive scale and precision engineering. The wheels themselves were typically 10 to 12 feet in diameter. The rim was iron, a continuous band of forged iron perhaps 6 inches wide and 2 inches thick. The spokes were heavy hardwood timbers, oak or hickory, perhaps 8 inches thick. A single wheel might have 12 to 16 spokes radiating from a massive wooden hub. The weight of one wheel was perhaps 2,000 pounds. 2 wheels plus the axle assembly brought the total weight to 5,000 pounds or more. The manufacturing of big wheels was specialized work done by companies that understood both heavy engineering and logging requirements. The wheel rims were forged in sections, then riveted or welded together to create the continuous band. This forging required substantial industrial capability, heavy forges, experienced blacksmiths, and quality control to ensure no weak points existed. A defective rim that failed under load could cause catastrophic failure with a 100-ton log suspended from the axle. The wooden hub was carved or built up from multiple pieces of hardwood laminated together. The hub had to withstand tremendous bending and twisting forces as the wheel rolled under load. The spoke mortises, the slots where spokes fit into the hub, had to be precisely cut to ensure each spoke bore its share of the load. Poorly fitted spokes would concentrate stress on a few spokes, leading to failure. The assembly used both traditional woodworking joints and iron reinforcement, straps, bolts, and pins that kept everything together even under extreme loads. The axle was solid iron, 18 to 24 inches in diameter, capable of supporting extreme bending loads. The axle length determined the width between wheels, typically 8 to 10 feet. This spacing provided stability and kept the wheels from interfering with the suspended log. The bearings where the wheels rotated on the axle were simple but massive, bronze or hardened steel surfaces with grease lubrication. The bearing surfaces had to be kept clean and lubricated because the loads were so high that any binding could damage the axle or wheels. The bearing maintenance was a daily task for big wheels crews. The grease would be applied liberally, pounds of grease per bearing. The grease had to be a specific type that could handle the pressures without squeezing out or breaking down. Some operations used custom grease formulations mixed on site from animal fat, mineral oils, and graphite. The bearings would be inspected for wear regularly. Excessive wear was evident from play in the wheel. If you could rock the wheel on the axle, the bearings needed attention. The lifting mechanism was the critical innovation. The big wheels didn't just roll under the log. They had a system for lifting the log once it was chained to the axle. The technique used a tong, a massive hinge device that gripped the log. The tongs would be placed around the log and connected by chains to the axle. Then, as the horse team pulled forward, the geometry of the chains and wheels would cause the log to lift off the ground and swing up toward the axle. The log would end up suspended at an angle, one end lifted high, the other end dragging on the ground. The tongs themselves were engineering marvels. Each tong arm might be 6 to 8 feet long, made from heavy iron or steel. The tong points that gripped the log had to bite into the wood without penetrating so deeply they damaged the commercial value. The hinge point, where the two tong arms met, had to allow the tongs to close around logs of varying diameter, from perhaps 3 feet to 8 feet or more. The tong closure was controlled by chains that could be adjusted to fit the log. The chains connecting tongs to axle were massive, perhaps 1 to 2 inches of link diameter. These chains had to withstand not just the weight of the log, but also the dynamic forces during lifting and movement. A chain failure, while a 100-ton log was suspended, could kill the entire horse team and any workers nearby. The chains were inspected regularly for worn links, cracks, or deformation. Suspicious chains were replaced immediately, regardless of cost. The physics of this lifting relied on leverage and mechanical advantage. The wheel diameter created a long lever arm. As the wheels rolled forward, the chain would wind up on the axle, not literally winding, but the effective chain length would shorten as the geometry changed. This lifting action required enormous force initially, but became easier as the log lifted. The horse team had to pull hardest at the moment of initial lift. Once the log was suspended, maintaining motion required much less force. The calculation of forces involved was complex, but understood intuitively by experienced crews. The initial lifting force required might be 20 to 30 tons, equivalent to the friction force of the log plus a component of its weight. And once lifted to the proper angle, typically about 30 to 40 degrees from horizontal, the force to maintain motion dropped to perhaps 10 to 15 tons, mostly overcoming the dragging friction of the suspended end and the rolling resistance of the wheels themselves. The operation of big wheels required skill and coordination. A crew of perhaps 10 to 15 men would position the wheels near the log. The positioning had to be precise. The wheels had to straddle the log at a point where the balance would be correct when lifted. Too far toward one end and the log would be too heavy at the dragging end. Too far the other way and the lifted end would overbalance the wheels. The foreman would judge the balance point based on the log's taper and density. The tongs would be placed and chained. This required men working around and under the log, positioning the heavy tong arms precisely. Once the tongs were set, the chains to the axle would be attached and tightened. The chain length adjustment was critical. Too much slack and the log wouldn't lift properly. Too little and the geometry would be wrong. The horse team, typically 6 to 12 horses depending on log size, would be hitched to the wheel assembly. The hitching arrangement used multiple eveners, wooden crossbars that distributed pulling force evenly across the team. A 6-horse team might use 3 eveners, one for each pair of horses, all connected to a main evener that attached to the wheel assembly. This arrangement ensured that if one horse pulled harder or softer than the others, the unequal force was distributed and didn't create unbalanced loading. At the command of the foreman, the team would pull. The initial pull to break the log's static friction and begin the lift was the critical moment. The teamster would command the horses to pull hard, typically with a distinctive call that the horses were trained to respond to. The horses would lean into their collars simultaneously, their combined pulling force perhaps 20 tons or more for a large team. If the log didn't start moving immediately, the teamster might signal for the horses to ease off momentarily, then pull again. The rocking motion of repeated pulls could break static friction more effectively than sustained pulling. As the log lifted, workers would watch the balance and the chain tension. If the log lifted unevenly, or if chains began to slip, the operation would stop and adjustments made. An unevenly lifting log could swing sideways unpredictably. Chains that slipped could fail suddenly. Any sign of problems required stopping, lowering the log, and correcting the issue. Once the log was properly suspended, the team would begin the journey to the landing. The journey with a suspended log was slow and deliberate. The typical speed was perhaps 1 to 2 miles per hour, a walking pace. The horses had to maintain steady pulling without surging or stopping suddenly. The load was heavy enough that any sudden change could shift the log's balance or stress the equipment dangerously. The route had to be cleared in advance, stumps removed, large rocks moved, paths graded reasonably level. Even so, the suspended log would strike obstacles occasionally. When this happened, and the whole operation stopped while men with pry bars and axes dealt with the obstacle. The grade of the route was critical. The horses could pull the suspended log on level ground or on gentle grades, but steep uphill grades were impossible. The load was too heavy. Steep downhill grades were dangerous. The weight could overrun the horses. The routes were surveyed carefully to avoid excessive grades. If a significant elevation change was unavoidable, the route would zigzag, trading distance for grade, similar to how mountain roads use switchbacks. The distance moved per day with big wheels varied with conditions, but might be 5 to 10 miles total. Several logs moved 2 to 3 miles each from cutting area to landing. This doesn't sound like much, but it represented moving perhaps 300 to 500 tons of logs total. And without the wheels, that volume couldn't be moved at all with available horsepower. Among the workers who operated big wheels was a man named Lars Jensen, a Danish immigrant who worked in redwood logging in California from 1895 to 1918. Jensen's letters to his family in Denmark, preserved by descendants, describe both the equipment and the work. From September 1902. I am working on the big wheels crew. The wheels are 12 feet high, twice my height. They are made of iron and oak and weigh several tons. We use them to move the great redwood logs. Today, we moved a log that was 65 feet long and 6 feet through. The log weighed perhaps 100 tons. I cannot comprehend this weight. We chained the log to the wheels and the horses lifted it. 12 horses, pulling together, lifted one end of that enormous log off the ground. Then the horses pulled the whole assembly 2 miles to the landing. It took 4 hours. This is the only way to move these giant trees. Without the big wheels, they would be impossible to transport. Jensen describes the challenges. The greatest danger is if the log shifts while being moved. If the chains slip, or if the log rolls while suspended, it can swing wildly. Men have been crushed by logs shifting. We must be very careful about the chaining and about maintaining balance as we move. The horses also are at risk. If a log breaks loose, it could fall on the team. The teamster must be very skilled to keep the horses calm and pulling steadily despite the massive weight they are moving. Another documented worker was Patrick Murphy, an Irish immigrant who worked as a big wheels foreman in Oregon from 1888 to 1912. Murphy's diary, it's preserved in a historical society collection, provides detailed observations about equipment and operations. From his diary, July 1895, "We received new big wheels today. They are the largest yet, 14 feet in diameter with an iron axle 2 feet through. The manufacturer claims they can handle logs up to 120 tons. The wheels cost $800, which seems extraordinary for 2 wheels and an axle, but the company says they will pay for themselves within 1 season by allowing us to move logs we previously had to abandon as too large to transport." Murphy describes typical operations. "A good day with the big wheels crew is moving 4 to 6 logs to the landing. Each log takes 2 to 4 hours, depending on distance and size. The limitation is not the wheels. They can handle any log we can chain to them, but the horses. 12 horses can move perhaps 80 to 100 tons at most. For larger logs, we must use 16 or even 20 horses, and coordinating a 20-horse team is very difficult. The horses must all pull together. If some pull harder than others, the team becomes unbalanced and the load may shift." The steam donkey engine revolutionized log transportation in ways that complemented the big wheels. While big wheels were mobile and could follow logs through the forest, steam donkeys were stationary but could pull logs over obstacles and through terrain where wheels couldn't go. The steam donkey was essentially a portable steam-powered winch, a boiler powering a steam engine that drove a large drum around which cable was wound. The typical steam donkey consisted of a boiler perhaps 4 feet in diameter and 10 feet long, a steam engine with a cylinder 8 to 12 inches in diameter, and a drum perhaps 4 feet in diameter, capable of holding 500 to 1,000 feet of steel cable. The entire assembly was mounted on a heavy wooden sled that could be dragged to a new location when needed. The total weight was 5 to 10 tons, depending on size. The boiler design for donkeys was simpler than locomotive boilers, but still required careful engineering. The pressure typically operated at 80 to 120 pounds per square inch, enough to provide power without excessive danger. The boiler tubes, the passages where hot combustion gases traveled through water to transfer heat, were arranged for maximum efficiency. The firebox would burn cordwood or sawmill waste. Anything combustible was acceptable. A donkey could consume a cord of wood per day or more during intensive operations. The boiler operation required constant monitoring. The water level had to be maintained within a narrow range. Too low and the boiler crown sheet, the metal top of the firebox, would be exposed to flame without water cooling it, leading to overheating and potential failure. Too high and the water would enter the steam lines, creating water hammer that could damage equipment. The engineer checked water level through glass gauge tubes multiple times per hour and added water as needed using a small steam-powered pump. The steam engine that drove the drum was typically a double-acting cylinder. Steam pushed the piston in both directions, providing power on both strokes. The cylinder size determined the power output. An 8-inch cylinder might develop 10 to 15 horsepower. A 12-inch cylinder might develop 20 to 30 horsepower. The engine speed was controlled by a throttle valve that regulated steam flow. The engineer could vary the pulling speed from a slow creep to rapid retrieval depending on operational needs. The drum design was critical to performance. The drum diameter and width determined how much cable could be stored. A 4-foot diameter drum might be 3 feet wide, capable of holding 800 to 1,000 feet of 1-inch cable. The drum had to be carefully machined so the cable would spool evenly. Uneven spooling would cause the cable to pile up on one side, potentially causing jams or cable damage. The operation of a steam donkey required a crew of 3 to 5 men. The engineer operated the steam engine and controlled the cable drum. The firemen maintained the boiler fire and steam pressure. The hook tender worked in the woods, attaching the cable to logs and directing the operation via signals. Additional workers called choker setters would attach the cable to specific logs using wire rope slings called chokers. The hook tender's job was among the most dangerous in logging. He worked at the end of the cable, sometimes a quarter mile from the donkey. His signals, hand gestures, or whistle codes told the engineer when to pull, when to stop, when to release. Miscommunication could result in logs moving when workers were in dangerous positions. The hook tender had to read the terrain, understand how logs would move when pulled, and position himself safely while still being able to direct operations effectively. The choker setters would carry wire rope slings into the woods to where logs were lying. A choker was a loop of steel cable with a sliding bell, a conical metal fitting that would tighten the loop when pulled. The choker setter would pass the choker around a log, thread it through the bell, and attach it to the main cable hook. When the engineer pulled, the choker would tighten around the log and the log would be dragged toward the landing. Setting chokers required working around and under massive logs in unstable positions. Logs could roll, shift, or have other logs piled on them. Injuries and deaths among choker setters were common. The cable yarding system used the steam donkey to drag logs from where they were felled to a central landing. The cable would be run out from the donkey through the forest, often for a quarter mile or more. The cable path would be established using blocks, large wooden pulleys, hung from trees at strategic points. The cable would thread through these blocks, changing direction as needed to reach the desired area. At the end of the cable, a large hook or set of chokers would be attached to a log. When the engineer engaged the drum, the cable would wind in, dragging the log toward the landing. The block placement was an art and a science. A block had to be positioned to direct the cable where needed, while avoiding obstacles the log would catch on. Blocks were hung from trees. The strongest trees in the most strategic positions were selected as spar trees or tailhold trees. A strap would be placed around the tree, perhaps 50 to 80 feet up where the trunk was still substantial, but branches were minimal. The block would hang from this strap. Installing blocks at height required climbers, specialists, who would climb trees using climbing spurs and safety belts to reach the desired height. The forces involved were tremendous. A large steam donkey might develop 20 to 30 tons of pulling force at the drum. With mechanical advantage from blocks, this could be multiplied to 40 to 60 tons or more. This was sufficient to move logs weighing 100 tons over rough ground, through brush, even uphill for short distances. The steel cable was typically 1 to 1.5 inches in diameter, capable of sustaining tensions of 50 to 100 tons before breaking. The cable paths through the forest created zones of extreme danger. The cable under tension would be as taut as a bowstring, vibrating slightly from the load. Anything that contacted the cable while under tension could be severed. A tree branch would be cut clean through, a limb or body part the same. Workers learned to never step over a cable under load, never walk near a cable, never position themselves where a broken cable might travel. The danger of cable yarding was extreme. The steel cable under tension was a lethal hazard. If the cable broke or if a choker failed, the cable would whip back toward the donkey with tremendous energy. Anyone in the path would be killed instantly. Broken cables were a regular occurrence because the loads and stresses were so high. Workers learned to stay clear of cables under tension and to never position themselves where a broken cable might travel. The cable breakage typically occurred at points of wear, where the cable passed over blocks, where it bent sharply, where it had been damaged by rocks or stumps. The cable would develop broken wires, individual wire strands in the cable that would break from fatigue. An inspector would examine cable regularly, feeling along its length for broken wires. When too many wires were broken, the cable would be retired from heavy service and perhaps used for lighter work. A cable might last a season or several seasons depending on usage intensity and conditions. The sound of cable work was distinctive. The cable under load would sing, a high-pitched vibration audible over the donkey engine noise. The pitch would change as load varied. When a log broke free from being stuck, the pitch would drop suddenly as tension decreased. When a log hit an obstacle, the pitch would rise as tension peaked. Experienced engineers could hear these changes and adjust pulling speed and force accordingly, reducing stress on equipment and cable. The landing where logs accumulated had to be organized carefully. Logs coming in from the woods would be stacked using peavies and cant hooks. The stacking had to create stable piles because the piles might contain dozens of logs weighing thousands of tons total. An unstable pile could collapse, crushing equipment or workers. The landing workers became skilled at judging how to stack logs for maximum density while maintaining stability. Among steam donkey operators was a man named James Anderson, a Scottish immigrant who worked in Washington, logging operations from 1900 to 1922. Anderson's account was recorded in an oral history interview conducted in 1950. He describes both the equipment and the dangers. According to the interview, I operated steam donkeys for 22 years. The donkey I worked most was a medium-sized machine, 12 horsepower steam engine, drum that held 700 feet of 1-inch cable. We could pull 40 to 50 tons with that machine under good conditions. The work was steady. Pull one log in, send the cable back out, pull the next log. We might yard 60 to 80 logs per day if the timber was close and the donkey was positioned well. Anderson describes the cable breaking. I saw cables break perhaps a dozen times over my career. When a cable breaks under full load, it sounds like a gunshot. The cable whips back so fast you cannot see it move. I saw a man killed by a broken cable in 1908. He was standing too close to the cable path. When it broke, the cable struck him across the chest and killed him instantly. After that, I was always very careful about where I stood when cables were under tension. But even with care, cable work is dangerous. The forces are so great that any failure is potentially catastrophic. He continued. The steam donkey itself was reliable but required constant attention. The boiler had to be watched continuously. If water level dropped too low, the boiler could fail explosively. We had safety valves, but they sometimes failed. In 1915, a donkey boiler exploded at a nearby operation, killing the engineer and fireman. The boiler was thrown 100 feet by the explosion. This kind of incident kept everyone alert to safety. You did not become careless around steam equipment. The combination of big wheels and steam donkeys created an integrated system for handling giant logs. The steam donkey would yard logs from the felling area to a main landing. At the landing, big wheels would be used to move logs the final distance to a railroad siding or mill. This division of labor used each technology for what it did best: the stationary power of the donkey for initial movement through rough terrain, the mobility of the wheels for final transport over prepared routes. Some operations became legendary for their difficulty and the ingenuity required. In 1910, a crew in Northern California moved a single redwood log that measured 84 feet long and 8 feet in diameter. The log was estimated to weigh 140 tons, 280,000 pounds. Moving this log required both steam donkey and big wheels working in tandem. The donkey yard the log from the felling site to a prepared route. Custom-built big wheels, 16 feet in diameter with a 30-inch axle, were used with a team of 24 horses to move it the final 3 miles to a railroad siding. The operation took 3 days and became famous enough to be photographed and reported in lumber trade journals. The cost analysis of log transportation reveals why the technology was necessary despite the expense. Moving a 100-ton log 2 miles using big wheels and a 12-horse team might cost $40 to $60 in 1910 currency, equivalent to $1,200 to $1,800 in modern dollars. This included labor for the crew, feed for the horses, equipment depreciation, and time. But that log might contain 60,000 board feet of lumber worth $600 to $1,200 wholesale. The transportation cost was 5 to 10% of the log value, economically acceptable. Without the big wheels, that log would be left in the forest, representing $600 to $1,200 of lost value. The technology made extracting giant logs profitable. The daily economics of a big wheels operation show the scale of investment required. A 12-horse team represented perhaps $3,000 to $6,000 in horse value, equivalent to $90,000 to $180,000 modern dollars. The daily feed cost for 12 horses doing hard work was about $3, $90 modern. A set of big wheels cost $800 to $1,200, $24,000 to $36,000 modern. The crew wages, perhaps 10 men at $3 to $5 per day each, totaled $30 to $50 daily, $900 to $1,500 modern. The total daily cost to operate a big wheels crew was perhaps $40 to $60, $1,200 to $1,800 modern. To be profitable, the crew had to move logs worth significantly more than this daily cost. The productivity required varied by operation, but might be 400 to 600 ton logs per day moved 2 to 3 miles each. This represented perhaps 300,000 to 400,000 board feet of lumber delivered to the landing daily. At wholesale values, this was $3,000 to $4,000 of lumber, equivalent to $90,000 to $120,000 modern. The gross margin, value of lumber minus costs of moving it, was substantial enough to justify the investment in equipment and horses. The horse teams that powered big wheels and performed other hauling were remarkable in their own right. A team might consist of 6 to 20 horses depending on the load. The horses were typically large draft breeds, Percherons, Belgians, Clydesdales, weighing 1,600 to 2,000 pounds each. A 20-horse team represented 20 tons of animal pulling together. The management of large horse teams required exceptional teamster skills. Each horse had to be in proper position, properly hitched, and responsive to commands. The teamster would drive from the front of the team or walk alongside, controlling the horses with voice commands and reins. Commands had to be clear and the horses well-trained. A single horse that balked or pulled incorrectly could disrupt the entire team. The feeding and care of large horse teams was a major logistical challenge. A draft horse doing hard work might consume 30 pounds of hay and 10 to 15 pounds of grain daily. A 20-horse team required 600 pounds of hay and 200 pounds of grain per day. Multiplied by a working season of perhaps 200 days, this meant 60 tons of hay and 20 tons of grain per team per season. Logging operations had to arrange for this feed to be delivered to their camps, which were often in remote locations. The economics of log transportation required careful calculation. Moving logs was expensive. It might represent 25 to 40% of the total logging cost. The big wheels cost $800 to $1,200, equivalent to $25,000 to $40,000 in modern currency. A steam donkey cost $1,500 to $3,000. The horse teams required continuous feed and care. Labor costs for the crews were substantial, but the alternative was leaving the largest and most valuable logs in the forest. A single old-growth redwood or Douglas fir might contain 50,000 to 100,000 board feet of lumber. At $10 to $20 per thousand board feet wholesale value, that single log was worth $500 to $2,000, enough to justify substantial transportation costs. The big wheels and steam donkeys made it economical to extract these giant logs, which made possible the large-scale harvest of old-growth forests. The transition from animal power and steam to gasoline and diesel power came in the 1920s and accelerated in the 1930s. Crawler tractors, tracked vehicles adapted from tank technology developed in World War I, could pull heavier loads than horses and didn't require feeding when not working. Gasoline-powered yarders replaced steam donkeys, offering more power and lighter packages. Trucks eventually replaced both big wheels and railroads for log transport from forest to mill. But during the transitional period from about 1920 to 1950, All these technologies coexisted. A logging operation might use steam donkeys for initial yarding, crawler tractors for secondary transport, and trucks for final haul to the mill. Or they might use big wheels for some operations and tractors for others, depending on terrain and log size. The choice depended on what equipment was available, what the specific site required, and what the logger could afford. The workers who operated this equipment, men like Lars Jensen, Patrick Murphy, and James Anderson, were specialists who understood both the capabilities and limitations of the technologies they worked with. They knew how to chain a log to big wheels so it would balance properly. They knew how much load a particular horse team could pull. They knew when a steam donkey cable was getting worn and needed replacement. This expertise was essential because the margin between success and disaster was often thin. Equipment pushed beyond its limits would fail, often catastrophically. The physical evidence of big wheels logging includes the trails that remain in forests where the wheels passed. The heavy logs dragging on one end while suspended from the wheels would create deep furrows in the soil. These furrows, sometimes several feet deep, would channel water and create erosion. In some old-growth forests, you can still find these trails a century later, recognizable as linear depressions in the forest floor that follow illogical routes, not following the land's natural contours, but following the logging routes from cutting area to landing. The legacy of these transportation technologies is the complete harvesting of old-growth forests. Without big wheels and steam donkeys, the giant trees of the West Coast couldn't have been logged economically. They would have been left standing because moving them was impractical. But with these technologies, every giant tree became harvestable. The economic incentive to cut them was strong, and the technology to move them was available. The result was the near-complete removal of old-growth forests from all accessible areas by the mid-20th century. The engineering innovations represented by big wheels and steam donkeys influenced later developments. The principles of using large wheels to reduce friction, of using cable systems to multiply pulling force, of organizing work crews around specialized equipment. These principles carry forward to modern logging equipment. A modern log skidder is essentially a mechanized version of big wheels, a powerful vehicle with a winch and grapple that can lift and transport logs. A modern cable yarder is a direct descendant of the steam donkey, a more powerful, but more sophisticated version of the same basic concept. The workers who moved 100-ton logs with horses and steam power accomplished something remarkable. They took technologies that seem inadequate, wheels made of wood and iron, steam engines burning cordwood, teams of horses, and used them to move loads that would challenge modern equipment. They did this through understanding the principles of leverage, friction, and mechanical advantage, and through skill developed over years of dangerous work. Today, if you visit a logging museum or historical society in timber country, you might see preserved examples of big wheels or steam donkeys. The big wheels look impossibly large. 12-foot wheels seem absurdly oversized until you learn they were used to lift 100-ton logs. The steam donkeys look crude and simple. A boiler, an engine, a drum. But they were sophisticated enough to perform tasks that required precise control of enormous forces. These artifacts are monuments to an era when moving giant trees required ingenuity and courage. 10 horses, 12-foot wheels, 100 tons of log, 2 miles through the forest, 4 hours of pulling. That was the reality of transporting giant timber in the era before modern equipment. The workers who did this work, the engineers who designed the equipment, and the teamsters who controlled the horse teams all understood they were doing something at the edge of what was possible. The logs were barely movable, even with the best available technology. But they moved them anyway, because that's what the timber industry required. The big wheels and steam donkeys are gone now. She's mostly replaced by machinery that makes the work easier and safer. But those earlier technologies represent a period when human ingenuity and animal power combined to accomplish tasks that still seem impossible. When you see photographs of 12-foot wheels lifting logs that weighed more than houses,